Okay, so let's recap what we've been talking about for the past 2 days. We are comparing arithmetic sequences versus geometric sequences. An arithmetic sequence is one that has a common difference, which means that you're consistently adding or subtracting by the same amount each time. So if you notice in the first one, as I go from -3 to 1, I'm adding by 4, and from 1 to 5, I'm adding by 4. That constant difference of adding by 4, which by the way comes from doing 1 minus -3 or 5 minus -1. You get a common difference of 4. Your very first term is -3. So if we wanted to make an nth term rule, so that's a rule to find any term of the sequence, the general rule for an arithmetic was a sub n equals a1 plus n minus 1 times d. Okay, so a sub n, which would be our nth term rule, a1 is -3 plus n minus 1 times 4. If I now have to use this to find a sub 5, it means you're plugging in n equals 5. So a sub 5 is equal to -3 plus 5 minus 1 times 4, and that comes out to be 13. Okay, so again, the benefit of making an explicit rule, and that's something we're going to talk about today, the difference between an explicit and a recursive rule, is that you can use the explicit rule to find any term of the sequence, whereas the recursive rule will have to know always the term just before. A geometric sequence has a common ratio. So if you take a look at the second example, it might be a little hard to see what am I multiplying by. I would say if you kind of just ignore maybe just the bottom and the top for just a second. So if I just ignore the bottom, if you see I'm doing 1, 2, 4, what am I doing there? I'm multiplying by 2. Or if I ignore the top for a second, 3, 9, 27, what am I doing on the bottom? I'm timesing by 3. So overall, what's happening is that I'm timesing by 2 on the top, and I'm timesing by 3 on the bottom, so that ends up giving me a common ratio of 2/3. If you can't see that, then what you would do is you always take the second term and divide by the first term. So in your calculator, type 2/9 divided by 1/3. I would definitely suggest using alpha y equals, hit math frac, and you'll see that that comes out to be 2/3, as would be the case if you did 4/27 divided by 2/9. Okay, so for a geometric sequence, the rule was a sub n equals a1 times r to the n minus 1. Okay, so if I need to make the nth term rule for this problem, my first term is 1/3. That's the first term in the sequence. My common ratio is 2/3 raised to the n minus 1. Remember, you never multiply these two numbers together. That defies like order of operations. You have to always do an exponent before you do multiplication. If I now need to find the fifth term here, I would plug in 1/3 times 2/3 raised to the 5 minus 1, and that comes out to be 1/243. Just to recall, arithmetic sequences are basically linear functions, except for the fact that you only are plugging in positive whole numbers in the domain. And geometric sequences are like exponential functions. That's the reason why you see these values get really small really fast or really big really fast. So again, in both these cases, these are what we would refer to as explicit formulas. Okay, what we're going to look at today is what happens when you're dealing with a recursive formula. So what makes a recursive formula different is that you have to be told like what the term is before the term that you have, before the one that you want. Okay, so if you take a look, and I'm going to use the definition on the left-hand side because I think that's going to be more like what you should expect to see. This is saying that we're starting with some term that the very first term is 3. Okay, then it says take the previous term. That's what you should think of when you see a sub n minus 1. The previous term, and add it by 3. So I'm going to take this previous term, I'm going to plug it in that space, okay? And I'm going to turn that into 3 plus 3. So my second term becomes 3 plus 3, and that comes out to be 6. If I need my third term, once again, I'm going to take the previous term, and I'm going to put that in the place of where that a sub n minus 1 was, and then I'm going to add that by 3. So when I do 6 plus 3 comes out to be 9. Okay, so if I try that again for the fourth term, I'm going to take that previous term, and I'm going to add it by 3, and then I get 12, and so on and so forth. You can see in this particular problem, eventually I get the pattern 3, 6, 9, 12, which eventually you could recognize as actually an arithmetic pattern, and then turn that into an explicit formula like we did during the do now. Explicit formulas will definitely be better and more useful for you. But it's important to make sure you understand recursive because the Regents sometimes ask questions about stuff like that. So if you take a look at the first example, it says write the recursive sequence formula for the sequences from the do now. Okay, so first things first, when you're writing a recursive sequence, you're always going to start by listing out what is the first term in that sequence. Okay, so whether it's arithmetic or geometric does not matter. You always have to list out what's the first place, what's the starting point for someone. Then the way you're going to express it is you're going to say, okay, the nth term comes from the previous term, and the way we're going to represent previous term is a sub n minus 1. And if you remember in this problem, we're constantly adding by 4 and adding by 4. So we're going to take our previous term and add 4, and that is now a recursive formula for that sequence. Again, if you have a choice, this formula, the explicit one, is definitely going to be better, because if you needed like the 100th term, you could literally plug in n equals 100 in place of that n. However, in a recursive formula, you would have to have the 99th term to get the 100th term. So that's why it's not as useful, but still we have to go over the way that these are created. For the other one, again, a sub n is always going to do something with the previous term, so a sub n minus 1. And if you remember, in this problem, we were always constantly timesing by 2/3. Well, you're going to take a sub n minus 1, and you're going to multiply it by 2/3. Okay, so those are the same exact sequences that we had in those previous problems, but now just represented as recursive formulas. I think you should be more prepared to evaluate a recursive formula than create one yourself. So if you take a look at a question like number 3, in question number 3 it says the nth term is equal to the previous term plus 5. So you're starting with a sub 1 equals 27. Okay, that, like previous term, is always going to get plugged in place of that a sub n minus 1. So the second term says, take the previous term and add 5 to it. And when I add 5 to it, that comes out to be 32. And then when I want the third term, I'm going to take the previous term and I'm going to add 5 to it. And that comes out to be 37. And then so on and so forth. And I continue. Now, this might be a thing that you probably want to get, be prepared for. It sometimes, again, might benefit you to take a recursive formula that's given to you and then eventually turn it into an explicit formula using arithmetic or geometric sequences. If you look at the pattern of what we have here, let me write it in different colors so it stands out. We started with 27, then we went to 32, then we went to 37. If you think about that pattern, hopefully it makes sense that 42 would be the next number. What are we doing here? We're constantly adding by 5. Again, that should make sense because it ties in with what was written in that recursive formula. The fact that you're adding by a value over and over is what makes it arithmetic. So if I wanted my nth term rule, it would be my first term, 27, plus n minus 1 times my common difference, which is the thing we keep adding by. So this would be what we call an explicit rule, whereas the one that we were given originally is the recursive rule. Why would you want to turn it into an explicit rule? Well, let's say you were given this recursive formula and you had to find the 100th term. I'm sure you're not going to want to sit here and do plus 5, plus 5, plus 5 100 times. This way, if you make an explicit rule, you can now just go right to plugging in n equals 100, and you'd be able to have the 100th term. Okay, take a look at the next one. So this one, I'm going to just change the notation a little. This is telling us, actually, let me go back to blue. This is telling us that the first term is equal to 64, and that the nth term is equal to 1/2 of a sub n minus 1, half of the previous term. Okay, so you're taking each number and timesing it by 1/2, and that gets you your next term. So my second term is going to do 1/2 of the previous term, 64. Half of 64 comes out to be 32. Then for my third term, I'm going to take 1/2 of my previous term, 32, and that comes out to be 16, and so on and so forth. And once again, just to tie this back in with stuff that we were talking about before, if you look at the pattern of numbers you see in this problem, 64, 32, 16, you can see that that comes out to be a geometric pattern. So if that's geometric, what are we multiplying by? We're constantly multiplying by 1/2, as you can obviously see from the rule given us in the recursive formula. So if we make our nth term rule, it's going to be a sub n equals our first term, which is 64, times the common ratio, which is 1/2, raised to the n minus 1. And again, that's the explicit rule. And again, it might benefit you to be able to change that into an explicit formula, so that way you could find any term of the sequence that you're possibly looking for. Okay, so let's do another practice example. If you take a look at question number 1, it says generate the next 3 terms given the sequence. So I'm going to rewrite this as a sub n equals a sub n minus 1 minus 8, where a sub 1 equals 10. Okay, so you're going to be starting with a sub 1 equals 10. Okay, this is telling you each time you take the previous term and you subtract it by 8. So the second term is going to take the previous term, which is 10, and subtract it by 8, so that comes out to be 2. So if I want the third term, I'm going to take that previous term of 2, subtract it by 8, and that comes out to be negative 6. And if I then want the fourth term, because it had asked me for the next 3 terms, then I take my previous term of negative 6, minus it by 8, and therefore the next 3 terms would be 2, negative 6, and negative 14. Now, I like the second part of this, okay, where it says, write an explicit formula for this situation. As I said before, if I now want to actually be able to use this recursive formula to find something else out, it helps me to have the explicit formula. So if you look at those numbers, I started with 10, then 2, then negative 6, then negative 14. What kind of a sequence is that? 10 to 2, you're minusing by 8. 2 to negative 6, you're minusing by 8. That's an arithmetic pattern because you're subtracting by the same number each time, or really you're adding by a negative number. So your nth term rule would be your first term, which is 10, plus n minus 1 times your common difference, which is negative 8, and that is now your explicit rule for this sequence, which will allow you to find any term of the sequence you could possibly want. Okay, let me just skip ahead. Take a look at example number 4. Write the next 3 terms in the pattern, starting with a sub 1 equals 16, and find the next 3 terms. So if I start with a sub 1 equals 16, this rule says take the previous term and times it by 3/2. So our second term is going to come from taking 16 and timesing it by 3/2. Okay, so if I times that by 3/2, 16 over 2 is 8, so 24. Okay, the third term is going to now take the previous term of 24 and times it by 3/2. Okay, so 12 times 3 is 36. And then my fourth term is once again going to take that previous term of 36, times it by 3. Okay, so when I do 36 times 3 over 2, that comes out equal to 54. Okay, so let's take a look at these numbers. 16, 24, 36, 54. If you tried to find a common difference, you would not find one this time. This time you're going to notice that if you took 24 and divided by 16, you're timesing by 3/2. Or 36 divided by 24, you're timesing by 3/2. So you now have a common ratio of 3/2, which once again, in this particular case, matches the number that was in that sequence, that recursive formula. So if I wanted an explicit formula for this, my nth term comes from my first term, which is 16, multiplied by my common ratio, which is 3/2, raised to the n minus 1. Okay, so once again, explicit formulas are great because they allow you to now find any term of the sequence, not just having to know the one that comes right before. So sometimes you can't express a sequence as arithmetic or geometric, but you can express it as recursive. So I'm going to go over some of these ones that are not necessarily going to come out to be arithmetic or geometric, and just talk about how would you actually be able to evaluate something like this. Once again, you can see that idea of reusing the previous term. This time, though, something that's going to be a little different, is you're also going to have to know what n value are you up to. Is it the second term? Is it the third term? Is it the fourth term? And so on and so forth. So we begin with t sub 1 equals 5. Okay, for t sub 2, it says take negative 1, multiply it by that previous term, and add whatever n you're up to. So negative 1, multiply that by your previous term, and add that to whatever n you're up to. So as I simplify, that comes out to be negative 3. So in the third term, it's once again negative 1 times your previous term, and you're going to add that by whatever n you're up to. Okay, so when I simplify, that comes out to be 5. And finally, the last one, because I was trying to get t sub 4, negative 1 times your previous term plus whatever your n you're up to, and that comes out to equal negative 3. Okay, and if you take a look at this pattern, you can see right here, 5, -3, 5, -3. This one actually ends up having a pattern that it alternates back and forth. But unfortunately, there's not really a rule for that other than this recursive sequence, unless you were to write something like, for even numbers, it's -3, for odd numbers, it's 5. But again, that's the idea with this recursive sequence stuff, is it allows you to write rules for a pattern that does not fit an arithmetic or geometric mold. Okay, so for the last one, number 6 says a sub 1 equals 7. This question says, do 2 times whatever term you're up to squared plus whatever term you're up to added by the previous term. Okay, so for my second term, I'm doing 2 times whatever term I'm up to squared plus whatever term I'm up to plus my previous term. Okay, and when I simplify that, that comes out equal to 17. So for my third term, once again, it's 2 times whatever term I'm up to squared plus whatever term I'm up to plus my previous term, and this one comes out equal to 38. And finally, my fourth term, it's 2 times whatever term I'm up to squared plus whatever term I'm up to plus my previous term. And you can see that this works out to be 74. Okay, so the first 4 terms are 7, 17, 38, 74, and unfortunately you will not find an arithmetic or geometric pattern that connects them. Your only way of writing